All right, so in Chapter 17, we're going to start our discussion with what are called Bernoulli Trials. And Bernoulli Trials are named after a man. His name is Jacob Bernoulli. This is him right here on this family tree. And he took part in a lot of statistics and mathematical discoveries. Some of you might recognize the name Bernoulli from maybe your physics class. So these are not the same Bernoullis. The man who we're talking about from physics class was Daniel Bernoulli. So same family. Daniel is actually Jacob's nephew. Okay? So the man we're talking about today is the uncle of the Bernoulli from your physics class. All right, just a little bit of trivia there for you. So when we talk about Bernoulli trials, there are three things you want to watch for. How you know something is Bernoulli. So here are three things we're looking for. When we're talking about Bernoulli trials, there are only two possible outcomes, success and failure. I put that in quotation marks because, I don't know, one example we might talk about is like having a kid. You get a boy or a girl. Now, which one of those is success and which one is failure, I guess just depends on your perspective. So they're in quotation marks because it doesn't mean one's good, one's bad. It just means success is the thing you're looking for, and then failure would be the thing you're not looking for. All right, the second thing, probability for success stays the same in every trial. So our probabilities are not changing, which takes us right into the third one, which is that the trials are independent. So what happens the first time will not impact what happens the second. And we do have this small caveat that says, well, even if the trials are independent, if you have less than 10% of the population, it's okay, we can kind of sneak past anyway. So a couple examples of things that are Bernoulli trials. Flipping a coin is the most common one. You'll notice when it comes to flipping a coin, there are only two possible outcomes. You can get heads or tails. The probability for, let's say, heads is the same for every trial. It's always 50%. And the trials are independent. What happens on one coin flip, if I get heads, that doesn't change what might happen on the second coin flip. Other examples might be foul shots in basketball and randomly guessing on a multiple choice test. You might think about those and how they fit all three criteria. So we're going to just do a couple examples here of, is it Bernoulli? We're going to think about those three things, okay? Thinking about two possible outcomes, probability is always the same, and that the trials are independent. So for each story problem, we're going to think about those three things. So here is my first one. You're rolling 5 dice, and you need to get 2 6s to win. Maybe this is a game. We need 2 6s to win. So are there 2 outcomes? As a matter of fact, there are. Now, I know you're thinking about dice. Oh, Miss Curtis, there's 1, 2, 3, 4, 5, 6. 6 different outcomes. But in this case, you're either getting a 6 or you're getting something that is not a 6. Because all we care about, right, are that we need 6s to win. So it's either a 6 or it's not. That's 2 outcomes. Let's see. Probability of getting a 6. Well, that's 1/6, and it's always 1/6 every time I roll a die. So that's fixed. It's the same. So we're good there. And let's see, independent. Yeah, each die, right, die, singular for dice. I have 5 of them. Rolling a 6 on one die does not impact what happens on another. So yes, this is an example of Bernoulli trials. All right, let's check out another one. All right, we record the eye colors found in a group of 500 people. Well, the first thing we're thinking about is 2 outcomes. And already I have a problem. There are more than 2 eye colors. Right, we've got at least brown, blue, green, hazel. I don't know what else there is, but that's more than 2. Now, if I had said I was looking for people with blue eyes, right, then it could be blue versus not blue, which is kind of what we did in the first problem. Okay, and then we could get away with it. But that's not the case here. We're just recording the eye colors, and there are more than 2 eye colors. So this one is not Bernoulli. All right, on our next one. A manufacturer recalls a doll because about 3% have buttons that are not properly attached. It's a horrible safety risk, right? A little kid could swallow a button. So customers returned 37 of these dolls to the local toy store. Is the manufacturer likely to find any dangerous buttons? Now, we're not going to actually answer this question. We're thinking about, do we have Bernoulli trials here? So, okay, I'll start with, do we have 2 outcomes? Well, I believe we do. There are either buttons attached, or we have buttons not attached. Those are 2 outcomes. Okay. The probability of success, or whatever it is we're looking for, needs to stay the same. Well, it says about 3% have buttons that are not attached. So the probability that the buttons are not attached, that's what we're looking for. I don't know that I'd call that a success, but it's what we're looking for. It's 3%. Okay, so that's fixed. There's like a 3% chance for every doll we pick up. And independent. Well, we do have like a certain number of dolls in the world. So it's kind of hard for me to say that they're independent. Once I find a lot of dolls with buttons, there are going to be fewer dolls. Once I find a lot of dolls with buttons not properly attached, there are going to be a lot fewer dolls that have that problem. So how I can get away with calling this independent is because I am only seeing 37 of the dolls. That is going to be less than 10% of all the dolls that were produced. Just a guess, right? I don't think toy companies only make 37 dolls. So this may or may not truly be independent, but because I have this less than 10%, I can get away with it. All right. So our last question says a city council of 11 Republicans and 8 Democrats picks a committee of 4 at random. So we're choosing 4 people. What's the probability they choose all 4 Democrats? Again, we're not looking at the question. I don't want to actually calculate a probability. I just want to know, are these Bernoulli trials? So I'm actually going to leave this one for you. Think about those 3 criteria. Are there 2 outcomes? Does the probability of choosing Democrats stay the same? And are the trials, or choosing each person, is that independent? All right, and before we stop, we are going to look at 2 flavors, I call them flavors, 2 different kinds of Bernoulli trials. Bernoulli trials alone are pretty boring, but if we put them together, we get things that are interesting. We actually get 2 different models. The first model is called geometric. So a geometric is where we're asking a question about how long until we achieve success, how long. So I really look for kind of a clue word of until, and these are the questions we did in Chapter 15. You might go back and look like the first Japanese car you see is the 4th car you choose. Right? That's how long until we see a Japanese car. So that's a geometric question. We're not going to spend a whole lot of time on those because we have already seen them. But the new model we're going to be looking at in the next section is binomial. This is when we're asked how many successes are in a set number of trials. So I think of these as the out of question. And we'll take a look at those in our next lesson.